Okay. Great. Okay. Sorry. Thank you. All right. So, hopefully most of you know me by now at this point. My name is Terrence Tricco. I am at the Memorial University of Newfoundland, which is in Canada, very easternmost part of Canada. Today, what I'll be talking about is parallelizing multiphysics, SPH, and phantom. I'll be outlining challenges and where we want to get to, but not really solutions to this problem. But I want to start with this question. Do you use MPI in phantom? Can I show of hands who's using MPI? One, two brave souls. Okay.
GitHub Actions put up its little hand.
GitHub Actions put up its little hand. Yeah, GitHub issues. So, but throughout the week, we've seen people say, I want to use APR to get better resolution. I am interested in getting a high number of particles to study fragments, highly interested in adaptive particle refinement. I need to improve my resolution, include adaptive particle refinement. I need to increase the resolution, Shamrock, and adaptive particle refinement. Cooling is not captured due to unresolved lack of SPH particles. Same terminology of I need more resolution. Apologies for my lack of photography skills on this particular one, but very high resolution is required, right? So we see a common thread, the thread through all of these, right? There's a clear need to run high resolution simulations. And people are turning towards APR as a way to do that, or Shamrock as a way to do that, right? But the need is high resolution simulations. And Guillaume spoke on Wednesday, and I really liked this slide, which encapsulates the many ways in which people need higher resolution simulations, right? They want high resolution to resolve the radius of a planet, or resolve a radius, or resolve something. They want to do higher integration, longer term integrations. They want more compute time for longer integrations, or more efficiency for longer integrations. They want to have more statistics to create a population of things so they get better statistics, or just run bigger things in general, right? So all sort of stems from we want higher resolution. So how can we reach higher resolutions in general? There's really two ways, from my view, of how to do this. One is algorithmic optimizations, right? A real like scientific computing approach of let's crunch the numbers in a more efficient and faster way. And the other is we'll just throw more things to crunch more numbers, right? And I really liked Timotei's talk where he just had the GPUs popping up like crazy, right? Just keep chucking more GPUs at it and we'll get it done through that route. But they're not at odds with each other, right? These are complementary approaches. Just a couple of examples, there's many more ways, but with algorithmic optimizations, APR, adaptive particle refinement, right? A 6 times speed up on one particular problem. You may get other speed ups on different problems, depending on what you do. And people are very interested in this because the 6 times speed up is great. That's great. That's like a factor of 2 in your resolution. Individual particle time steps is one that's been in phantom for a very long time and that we're all sort of accustomed to. But depending on your problem, you can get a factor of 100 to 1,000 times the speed up. Imagine going from like 1 node to 1,000 nodes, right? That's taking us into exascale territory. Individual particle time step is already that 1,000 times improvement. So we don't want to lose these sort of things. On the compute side, and I have sort of broadly broken down into 3 classes here, depending on the hardware architecture. I apologize that it's on the low part of the slide. OpenMP, been in Phantom for a very long time. Phantom has very good OpenMP scaling. I can take 1 node, I can utilize all the cores on that node, and I can get as much efficiency as the number of cores, which is on the order of 48 to 64 for what most people have access to. MPI depends on how many nodes you use. Factor of 2. If I use 2 nodes, maybe a factor of 1,000 if I have those resources and my implementation lets me scale that well. And then GPUs, I have the number here for like a single GPU. Could be a factor of 2, could be a factor of 10. Somewhere on that order is sort of the promise or where we're hoping to get to. And these things can all kind of be combined, right? We can do APR with individual time steps on an MPI or an OpenMP node with 64 cores times 1,000 nodes with 1,000 GPUs, right? That's kind of the dream of where to get to. And Shamrock and the Shamrock folks, they're doing a great job with that. I like the idea that the Shamrock moment is heading in that direction. So how many people use Phantom MPI? We got one or two brave souls. How good is Phantom's MPI scaling? And I feel really bad to do this. And I apologize to Daniel that we're like airing dirty laundry in like a public way, but it's highlighting the challenges here. So I ran a simulation. This is a simulation. This is the movie. It is actually going. We have a ball of gas and it's gravitationally contracting. That's the end of the movie. That's where it stops. I don't go farther than this. It's just a ball of gas that slightly contracts. That's it. That's all I've done. And I ran this with two, just the pure OpenMP imitation on the left-hand side with 64 cores. And on the right-hand side, 120 cores using two MPI nodes of 64 cores each. With the OpenMP imitation, I get a ratio of 53 CPU over wall time. Very nice. With MPI, I get a ratio of 99 CPU over wall time. Great. It's like a factor of 2. But when you take a closer look at the efficiency here with the single node, I'm computing about 500,000 particles per second. And then I double my compute power and I'm computing about 100,000 particles per second, as in the MPI is 5 times slower for this problem. Right, so there's challenges here in how you handle communication. Daniel?
Extremely selective in the sense that
it is extremely selective and biased, and
so specifically self-gravity is the worst case.
Yeah.
So the things that do show speed up, I mean, there's a talk on the channel actually from David Conrad, but the like non-self-gravitating disk scales all right.
Yeah, and so that's my next slide. Right, so like one challenge, and the challenge that I focus on is the multiphysics challenge, right? Like, and to Daniel's point, right, and to the demonstration of Shamrock. Shamrock has demonstrated hydrodynamics, just pure hydro, 500 billion particles, and they can get that scaling, right? That's really impressive. But how do you do that if you include gravity and you include dust, 1 fluid, 2 fluid, multi-grain growth? Seen lots of variants of different dust algorithms throughout this conference. Magnetic fields, relativity, you add radiation, flux limit diffusions, and phantom. Add sync particles, those sync particles, I think, scales. Winds, chemistry evolution. The chemistry evolution is very complex. We've heard talks about that, et cetera, right? There's lots and lots of physics that are in phantom that are really important to the vast majority of people in this room. So how do we have that scaling and include all these kind of physics? So this is where my interest is, right? I'm very interested in parallelizing multi-physics SPH simulations. The algorithmic optimizations are important, but we need to combine those with the ability to add more compute. Because if we can have like the Shamrock style of 500 billion particles running on 1,000 GPUs, and then you put individual particle time steps on that, and then you get another factor of 1,000 times faster. Just think, like, let that sink in for a moment, right? So all these things got to work together. And I think one very important area is GPUs, right? We've had talks, Timothy, Andrew, Tom have given talks about GPUs and how to port SPH on GPUs. And I think this is very important because if you look at, so the top 500 list is the list of the top 500 most powerful supercomputers. Probably many of you are familiar with that list. They also have the top 500 green, or the green 500 supercomputers. So if we look at the top 200 green supercomputers in terms of their energy efficiency per computing, we can break this down into, do they have a GPU component on their supercomputer, and do they not, right? So the blue dots have GPUs, a GPU component, and the orange dots do not. And it's very, very striking to me, the energy efficiency of the machines that have GPUs, right? The CPUs are all down here in this orange region on like 10 gigaflops per watt or less, and the GPUs just scale upwards from there by factors of 2 to 5 to 7, right? It's very, very striking, the divide. And so you want to be programming for GPUs because they're very energy efficient, and clusters are increasingly adding more GPUs to them for that reason, in addition to like AI, machine learning use, and so on. We want to make sure that we're using GPUs because that's what supercomputers have. And so if we look at the trends of CPUs over the past 50 years or so here, I hope everybody's familiar with Moore's law. The idea of Moore's law is that like computing power increases by a factor of, or it doubles every 2 to 3 years roughly. And that's basically consistent with the number of transistors on your chip, right? The number of transistors has just exponentially increased over time, and it's just always done so. And the benefit of that is that if you were in the 70s and 80s and 90s and you wanted a faster computer, well, you wait 2 years, and my computer is now twice as fast. And because the transistor counts kept increasing, you can have single core machines. I didn't need to use more cores. I could just do everything on a single core, right? 10 to the 0 is just 1. I have a single core. Until the frequency of your CPUs cannot be increased further. So how do they add more transistors? They start adding more cores. At the very start, this transition point right here. They keep adding more transistors, but they do that by adding more cores. So this is for a CPU, and right here around this point, you're looking at 64 cores, which is kind of the world we live in today. If we look at the same plot in terms of number of cores for GPUs, and I've selected NVIDIA desktop GPUs, just this one line of GeForce NVIDIA GPUs, right? The number of cores is vastly different. In the early 2000s, we're looking at like 10, 12 cores, but that just explodes 10,000 cores on an RTX 4080. So they're very, very different architectures to program for, right? Because you have 10,000 cores versus 64 cores or 100 cores, or you're looking at a factor of 100 roughly. And then that's just the core count that's different. There's also other architectural differences in terms of memory and so on. So do I have answers? No, not really. But I think this is the direction we have to go in, is for GPUs and adding in multiphysics. We're looking for the solutions on these problems, and we've heard people talk about it in this conference as well. So some short-term goals that I have for improving the parallel performance of Phantom. These are short-term goals for the next, say, few years, hopefully. Use 1 to maybe 4 GPUs, depending on if there's more than 1 GPU per node, to increase compute, right? Most HPC nodes have an attached GPU. And so when you reserve a node, and I say, I want all 64 cores of this node, okay, there's a GPU that's attached to it that is now blocked, that like other people can't use, and it's just sitting idle and just wasting it. So we want to make sense, I can take a node and use a GPU that's attached to it. That's not too hard of a problem, and I know it can be a hard problem, but I think it's a solvable problem of I have CPU with RAM and I have a GPU with RAM, and there's just like one communication back and forth. Short-term goal is to make this work with individual particle time steps, and that's what Andrew Harris talked about a few days ago. My benchmark for this is that if I compile Phantom and I say GPU equals yes, it doesn't go slower. I am happy if it goes faster, but worst case, it shouldn't go slower. That's the short-term goal. And then NPI scaling, and this is also seems like a low goal, with NPI scaling to 4 to 8 nodes. Because I think if we can combine 4 to 8 nodes with 1 GPU, then you're looking at going from a 5 to 10 million particle simulation to a 50 to 100 million particle simulation. So I have an engagement with the HPC consortium in Canada around this, around the parallel implementation of NPI. We'll see how well we progress on that. So just to summarize, we're working on NPI and GPU angles to increase Phantom's parallelization while retaining all the things that Phantom currently does. So I think that's really important in retaining these algorithmic optimizations and all the physics that are there. I did not speak about this at all. I thought about cramming MHD stuff into my talk because I'm very interested in MHD things. Jackson spoke a few days ago about MRI, global disks, and that's a fantastic workshop for us because we plan to use Shamrock for that to increase our compute as a way to do that. But I also have another student working on magnetized white dwarf mergers who couldn't be here, but there's a whole talk I would love to give about that. But just, focus on this instead. So I'll pause here, and if you have questions, happy to take them. Thank you very much.
Terry, so do we have questions from the audience? I can start. I guess it's more of a comment. So it's more of a comment. When you show us the graph of the green systems.
Yeah.
So what we're looking at on the left is gigaflops, and in my experience, and I suspect that yes, they can do an awful lot of calculations, but most of the things being run on those nodes are achieving much less in terms of actual output per gigaflop. So coding efficiently on a GPU, it is still much harder to get the best out of the gigaflops that you have. So it's just aware. I agree with you in nearly every way, but I think it's a lot less extreme than that graph might suggest.
Yeah, and just to comment on that, like I think a good example of what you're saying is if I want to compute gravity, I can do it in a brute force n squared way, and I can get fantastic scaling. But it's a really stupid thing to do because it's going to take forever, even though it's like really efficiently just a bad computation. Yeah.
Okay. But on the same topic, actually, if you do the same graph with instead the bandwidth per watt, you will get actually the same exactly the same curve. Like one of the advantage of the GPU is that because it's massively parallel, you actually can exploit the full bandwidth of the large memory architecture, especially HBM memory. And turn out that especially for SPH and hydrodynamics in general, the speed up we gain is not from the increased compute, but actually from the increased bandwidth. If you were like to, I did it for Shamrock, but if you were to benchmark it on like many architectures and compute the actual bandwidth of the architecture, the speed up is literally the factor in bandwidth, and it's on the line. I've not made a specific plot for this, but it's like exact one-to-one.
So you're suggesting that SPH is bandwidth bound?
It's totally is, and IO in general is.
There's lots of optimizations in Phantom to increase like caching and memory and things like this, so that it stays closer to the CPU rather than RAM. I think this kind of idea, yeah, related to that anyway.
Other questions? Well, if not, let's thank Larry again.